So what we are seeing is that this is the blue thick line. Can you see my screen?
Uh-huh. Yeah. That the PQ, that line.
Yeah, the curved
The
PQ
curved
is the
drive.
actual function. No, the curved PQ is
Yes.
probably a function which is z equal to f of x and y,
Hmm.
right?
I, I,
Because
yes.
otherwise, I mean, you cannot have this here. In 3 dimensions, you can only have z equal to f of x comma y.
Hmm. Yeah.
So that is this function. Then what is it saying? It follows that if C is the curve determined by the intersection of the graph of f and the
Hmm.
plane P, so the graph of f may intersect the plane P in only 2 points. It may not even intersect in a curve. How is it saying it's a intersection?
Like,
Understand this. Okay, let's just move forward and see what they are saying.
yeah. I'm not able to understand that yellow region. Like, how what's the shape like? How many points it's passing through, and all that stuff.
So probably this yellow region is a surface. So is z
Hmm.
equal to f of xy? Is this oh, that's a surface, right?
That's
Is,
a surface.
is this like, does this defines a surface? Oh
Yeah.
yeah, it defines a surface, correct.
Surface.
Corresponding to
Yes.
every point on the xy plane,
Yeah.
we have a point zy. So this defines the
Huh.
surface, right?
It defines the surface. Yes.
This defines the surface, and therefore the intersection of the surface
Huh. With that,
with the plane that
the
contains that straight line, this plane, vertical plane,
that's the directional directive.
that will that no no
Oh, acha.
that will be the curve PQ. So there is some curve
Okay.
PQ in that plane.
Okay.
And then what is it saying? It follows that if C is the curve determined by the intersection of the graph of f and the plane P, then this thing, the limit, the function at Q minus the function at P divided by H would be the
Hmm.
slope of the line tangent to C, tangent to the curve, tangent to the curve PQ
Yeah.
at x0, y0, and z. Basically at xyz. At that point
XYZ.
xyz.
Hmm.
Oh, okay. Okay, so that's because if P and Q are very close to each other,
Yeah.
the curve, you will not see any big changes in the curve. It will actually be like just like this only, very
Hmm.
small.
Yeah. It will
So
be
if it,
small.
so if it's like very small, then the tangent here, the slope of the tangent here can be found by calculating Q, the value of the function at Q minus the value of the
Yeah.
function at P and
Minus
divided by the
value
difference.
difference. So that will, yeah, that's correct. Yeah, that will give
Right?
us that.
Because they are not
Yeah.
far away, right? They are not far away that f of
No,
q
no.
minus f of p will be different from, like in this case, fq minus fp divided by f
Yeah.
will be different from the tangent here.
Tangent.
But
Yeah, it won't be that. Yeah, but like, oh, in that case, it might be, but here
just,
it won't be that.
just 1 minute, I'll come back.
Yeah. Yeah.
then that is the tangent, that is the slope of the line tangent.
Yeah.
Because of the intimate relationship between derivatives and slopes of tangents for functions of one variable, we are led to refer to the limit above as the derivative of f in the direction.
Hmm.
Okay, so we are saying that this, oh, so what they are saying is in one dimension we have seen that the derivative, what the derivative means is the slope of a tangent line. Derivative
Hmm.
means slope of the tangent line in one
Slope of the tangent line in 2D. Yes.
in 2D, isn't it?
Yeah.
So here also
Yes.
this particular derivative means the slope of the tangent line, but slope of the tangent line in that direction, in the
Uh,
direction a1I plus a2j.
hmm. Correct.
Mm,
That should be.
yeah, a1I plus
Yeah,
a2j.
that's A to J.
But this is, mm, but I am still not convinced, but maybe we can read on. I'm still not convinced because the point P and Q may not be in a plane parallel to xy plane.
Hmm.
So Q might be in a higher, Q might have a higher z value, P might have a lower z value. Okay, so
Hmm.
are you understanding? So PQ might be something like
Uh,
this. Even though the distance between P and Q is very small, it's h,
okay. But PQ distance will be like that.
right? But still, if P and Q are not in the same plane,
Yes.
why should we assume that, if this is the curve, this is that curve produced by the intersection of that vertical plane. There's a
Hmm.
vertical plane like this, right?
Yeah. Correct.
With some surface, some yellow surface was there.
Some surface.
Like there was some yellow surface was there. So the yellow surface and the green plane are are intersecting and producing.
A
Oops.
small section of this thing.
Right. That red arc.
That yes.
That red arc is such that it that red arc contains the points P and Q.
Uh,
But the points P and Q, both of P and Q points may not necessarily be in this horizontal plane, which is parallel to XY.
hmm. But can be in a vertical plane.
Yeah, P and Q are in the green plane, right?
Yeah, but
But
Q won't
Q
be in the red plane.
Q may not be. I'm saying Q may not
Okay,
be in the
may not be.
in the horizontal red plane. So why are then they saying that the the change between Q and P, right? F of, so this is essentially F of Q. This is F
Mm-hmm.
P divided by H. Why should this is like the slope of the line tangent, and the line tangent itself, that tangent line itself is this tangent line, which is not necessarily in the x in a horizontal plane,
True. Yeah, it won't. Yeah,
right?
won't be.
So
Yes.
then why are we led to refer to the limit above, this limit, as the derivative of f in the direction? So that direction does not have a k. It's in the x.
Ah,
This
yeah.
direction is in k.
Hmm.
Why should this tangent be in a horizontal flat direction? This change. That's what I'm not 100%
Yeah,
convinced.
that's correct. Yes.
So then let's see what they're saying. Definition. Let f be the function defined on a set containing a disk D centered
Mm-hmm.
x0 y0, and let u be a1I plus a2j. Then the directional derivative of f in the
It is that
direction u is given
hmm,
by this directional
that
derivative
formula.
of
Yeah,
in that direction
it is something similar to like how we had in like finding a derivative only using limits. If you had to find something similar like that, but no, again here they're using formulas for x0 plus ha1, y0 plus ha2, that thing. So that we have to plug in the function, and then that's how they find that. Okay. So is directional derivative like one form of like finding the like finding a tangent of a curve like that in 3D? Is it like that exactly? Like by looking at the formula, I was just wondering.
okay, I think what they are saying is
Yeah.
our doubt oh, is
Hmm.
not as great. What they're saying is okay, let's in two dimensions, what do we do? In two dimensions,
Yes.
this is our
We
curve and
correct.
we are traveling between 2 points. The points are really close to each other. Then we draw the tangent
Yes. Yes. Correct.
PQ. So we are saying this is the derivative, the
Derivative of curve.
function at Q minus function at P divided
Yes.
by the x difference.
Divided by that distance. So like, yeah. How do we find the distance again? Like
X
using
distance h,
x distance, edge distance. Okay. Okay.
limit h tends to 0. We say this is the derivative dy dx.
Absolutely. Correct. Exactly. This is how we did know in derivatives like back then. And now I'm seeing this formula. It looks pretty similar.
Yeah, it looks similar. So of course the y is not the same. The y is different. This is y1. This is y2.
Ah,
But this is a tangent. This is the direct. This is the derivative. This is the derivative at x, right? This is the derivative at this point x
hmm.
or at x0. Okay, so they are saying the same thing even here, right? Even here,
Yes.
okay, they are saying the same thing. Wait, I'll-
Yeah.
what they are saying is, of course, P and Q may not be in the horizontal plane. Q may be a little bit up there, right? And that is so that is why see f of what is f at Q? F at Q is essentially Z at Q
Z at Q.
because remember this is our function Z. Z itself is our function
Correct.
in
Yeah.
this case.
It is our function. Correct.
So Z of Q minus Z of P
Hmm.
is the numerator.
Yes.
Is
Yes.
actually the numerator in that term. This numerator. It's like Z at Q minus Z at P, right? Z of x0, y0, and this is Z of at a different point.
Hmm.
And the divided by what? Divided by this distance. This is h. And h has been that h divided by that h
Yes.
has been traveled in this direction, right? H has been traveled
Ah.
in that direction. This is
Correct.
h. And so we can say that this is the derivative, and we are only saying that this is the derivative in this direction because the
In that.
derivative, yeah, okay, because the derivative in some other direction will be different.
Hmm.
If you are saying derivative in some other direction means you will go like this on the surface.
Yes.
You
Yes.
this might
Yeah.
be q dash. So the derivative in some other direction may be different because q dash, sorry, q z of q dash may not be the same as z of q. So like the difference between the z coordinates here and the difference between the z coordinates here may be different. So the derivative in this direction, derivative in that direction may be different. Is this making sense?
Yeah. To yeah. Then that formula is there again for finding the derivative. Okay, that is like if no, how are they taking the power? Oh, okay, no, that's different. Okay, yeah, the formula is like finding the partial derivative of this. So it's like same thing as I think that if our unit vector is u of ai plus a2j, a1i plus a2j like that. Okay,
I think
that was the
is
formula.
it clear or not? So
Huh.
3D view of a surface. Let's
Hmm.
catch some. Let's just copy some picture somewhere. This one.
Yeah. Hmm. Yeah, the graph I see.
Okay. Now there may be two different straight lines. One straight line
Hmm.
is like this. Oh, it's not. If you draw a straight line over a picture, it will not draw it straight.
Oh, that's weird.
So if this is the straight line, if this is one of the straight lines,
Ah.
this is uh, let's say this one is okay, I'll draw them one straight line like this. Now this is in the
Hmm.
xy plane. One straight line
Yeah.
like this, and one straight line is like this.
Okay. Yeah.
So correspondingly, some point just above this here, and some point
Mhm.
just above this here. Okay, and
Yeah.
we should actually make them very close to each other, but here for illustration, we are not doing that. They're quite far away. So the tangent will be something like this. I mean,
Hmm.
the change in h is like this. It's more or less a flat kind of a tangent. It's like
Flat kind of.
almost no change. But
Yes. Okay.
if you do that, if you take one point here along this line and go to the top, it's here, and you
Uh-huh.
take one point here, right? Then it looks like this is going up
Correct. Yeah. That's how
because of the
it's
surface.
correct.
This surface is like
Yes.
that. It's going up as you move towards the center. So
Correct. Yeah.
along,
Absolutely.
so in this direction, the tangent has some maybe I mean it looks like the slope is some plus one, right?
Ah.
And here
Yeah.
looks like the slope is zero.
Hmm.
I mean the slopes are different. At least we can say that. Right? So the derivative in different directions are different. That's the conclusion.
That's okay.
The derivatives of a function, derivatives um, on a surface in different directions are different.
Okay. Yeah. Yeah. Correct.
Different directions
Yeah.
are different. They have different values, and hence the concept of directional derivatives.
Hmm.
So now let's move forward. I mean, this is some derivative in some direction, and there can be some other derivative in some other direction.
Yes.
They are saying d, the derivative along the unit vector small, this u subscript denotes the particular unit vector is given by this. You have to travel along that line to get that derivative. right? You have to evaluate the function from this point and traveling like a1h in the x direction,
Yes.
a2h in the y direction.
Y direction. Okay.
Now what they're saying, observe that if the unit vector u is just I, this is clear, so we can go for.
Yeah, that is clear. Yes.
Now they are
That's,
saying if the unit vector u is just
hmm.
one I. By the way, this is a unit vector, so a1 and a2 cannot have just any random values. Their values of
No, that's true. Yeah, it will be something like the direction. I think no, the of the unit vector. I think
their values will be limited by this formula,
absolutely. Yeah.
unit vector, right? So like it can only be, cannot be one I and two j. It can only be something like this or something like this,
Hmm.
so that a1 square plus a2 square is 1 always.
Got it. Yes.
Basically cos alpha I plus alpha.
Cos alpha I plus sin alpha I. Sorry, J. I mean, yes.
This is how I,
That's how good. Yeah. If you find that thing, yeah, it will be the same. The angles and all.
like a unit vector will always have this limitation. So now they're
Yes.
saying let let it be the case that
Hmm.
that we are trying to find the directional derivative along this direction. Okay, let you can find the
Okay.
directional derivative along any direction you want. You can find it
Hmm.
along this direction, this direction, this. These are the different directions, and that is how the alpha comes into play. The alpha tells you the direction, angle alpha.
Hmm. Alpha. Okay.
So let it be the case that we are now finding the directional derivative for u equal to I. What does it mean?
Hmm.
It means they are taking this direction. This is u equal to I direction.
Yes.
Okay, u equal to
Correct.
I direction. So what will be the unit vector in if, oh, unit vector is already given. U is I. This is the unit vector.
Hmm.
So then a1 is 1 and a2 is 0, right? A1 is 1 I, it's 1 I. Basically, it's
Hmm.
I. So the a1 is 1, a2 is 0.
A2 is 0. Yes.
A1 I plus a2 0. So obviously, if you match them, a1 is 1, a2 is 0. Okay.
Yeah.
Then what
Okay.
happens? So then, if you plug into this thing,
Hmm.
a1 is 1, a2 is 0. So it becomes f
Yes.
of x0 plus h comma y0 minus, this is the same thing, by h. Now observe what this is. This is nothing but only the x changed. Y did not change.
I did not change. Okay.
Along, if you're traveling like this, if you're traveling along x direction, only x will change, y will not change.
I
So,
will not change.
so this expression, sorry, this expression is actually fx, the partial derivative of the function
Hmm.
with respect to x at the point x0 comma y0. That's a different, it's at x0 y0.
Okay.
But what it is the partial derivative along x. Basically it's tau f tau x, something as fx, dou f dou x, the partial derivative dou f dou x, which is also denoted by f subscript
Hmm.
x at the point x0 y0.
X0 Y0. Yes.
This is what the directional derivative is if you are traveling along u equal to I. Similarly, If you were to travel
Hmm.
along u equal to j, then the partial derivative would be f subscript y.
Hmm.
Okay, because then the x0 will remain the same
Yeah,
and y0 will change. Because then
will
a2 will
change.
become 1, a1 will become 0. Yeah.
Zero. Okay.
So then what? Thus the first partial derivatives of fx and fy
Mhm.
are
Yeah.
special cases of directional derivatives. These are actually directional derivatives along those particular directions. Fx is a directional derivative along I. Fy
I.
is a
Yes.
directional derivative along j
J. Ah, okay.
in the directions of the positive coordinate axis. If it turns out that if f is differentiable at x0, y0, then any directional derivative can be evaluated by means of the two partial derivatives. That is,
Hmm.
now they are claiming that duf, the directional derivative along any arbitrary direction a1i plus a2j is simply equal to a combination of fx and fy. And how are they combining fx and fy? Whatever is a1 is multiplied by fx, whatever is a2 is multiplied by fy, and then they add it. And then they say this is the directional derivative along any directional a1i plus a2j. A1,
E to J.
this is a unit vector.
Yes. Correct. Okay.
Oh, I thought they were not giving the proof, but there is a proof also here.
There is a proof also. Yes.
Okay, it's just 1 minute.
Yeah. Yeah, no problem.
Yeah, hello, Ayush.
Yeah. Yeah.
So there is a proof also here,
There is a proof.
but
Yeah.
shall we can skip it? Okay,
Yeah. We can. Yeah.
because it looks like obvious
It's
that
like obvious. Yeah. Actually, I was reading through it. Yeah. It was like f of h and all f of h minus f of 0. So that's how they proved it. And yeah, I basically gone through that. Then there are example questions, I think. So it's like that only. So
yeah,
f of x.
I was still writing this because the notation can be, see, this is directional derivative capital D in the direction of
Capital
unit
D.
vector u of the
Unit vector
function
direction.
f. See, the directional
Yeah.
derivative in the direction u of the function f at the point x0 y0,
And yeah, correct.
okay, is equal to the partial derivative of f with respect to x at x0 y0 multiplied
Mm-hmm.
by a1, where a1 is part of u, right? U is
Yeah.
a1i plus a2j,
U is A1 I plus A2J.
and similarly fy x0 y0.
Mm-hmm.
So, okay, after this, there are some examples. They're saying fx is given by this, u is this, find this. Okay, let's do it
Mm.
ourselves.
Yes, yes.
So this is this. And
Hmm.
what is the directional derivative
And
du of the function?
our du of function f1 2. So I think it will be fx of 1 to I plus plus fy of 1 to g.
No, no, no. It's
Then
there's a little bit of a. It is not I and j here. The
oh
direct. First of all, the directional derivative
a1. Sorry.
a1
I saw the formula. Yeah, because I mistook with that u of ai plus a to j in the part.
and
So it will be a1.
yeah. So what is a1 and a2?
So a1 and a2 will be that. I think a1 a2 is this thing. U that u vectors a1i minus a2j, right? So
Hmm.
it will be 1 by root 2
Hmm.
and minus 1 by root 2.
Minus 1 by root 2. What about I and j? Would you still have I and j here?
No,
No, because the directional derivative is not a vector
it's
quantity.
it's not a vector points like finding. I think it's like a number you'll get in the
It's
end,
a
like a constant
number.
value.
Yes, it's a number.
Yes,
It's a slope of some tangent line. It's a number.
it's a slope. Yes.
Okay, so it's not a vector. Okay, so then,
Hmm.
okay, can you find fx?
Fx of 1 2, yes. So that will be that's gonna be 0 minus 6x
Hmm.
minus 0.
Yes, and of 1 2 means
Of 1 2 it will be 6.
minus 6 or plus 6.
Minus 6.
Minus 6.
Minus 6.
And
Yes.
fy at
And
1 2
y at 1 2 it will be like 0 minus 0 minus 2y. So 2 2s are 4. Minus 4 actually.
minus 4. And then we plug that in here. Fx is minus
Yes.
6 by root 2
Minus 6 by root 2 minus 4 by 2. So
because
that
we have
gives
a,
us, yeah.
yeah, this will
Hmm.
become plus, right? Because
Oh, yeah, because the negative is also there for minus 1 by root 2.
so it becomes negative
Minus 2 by root 2. So that's minus root 2.
minus root 2.
Root 2.
So the directional derivative in that direction in this direction is negative root 2.
Minus root 2. Yes. Right.
Okay. So is this away at this in the direction of A?
Yeah.
This is another example which is going to be slightly different, only
The
slightly.
next one.
Yeah.
Okay. So that's like, let's say f of xy is equal to xy square is I minus 2j. Find the directional derivative of f at minus 3 1. Because this time it's our unit vector. I think it's
Hmm.
simply a. It's like just a normal vector. So we need to just we need to just normalize that thing. I think.
Right. So what is the unit vector? What is
So
going to be the unit in
so
A?
it will be u. Yeah, it will be like u a is it will be like a that vector a divided by the magnitude of a. So like yeah, that is I minus 2j by what it's gonna be root of 1 square plus minus 2 square. So like 1 plus 4 root 5. Yeah, that will be our u. We can, yeah, 1 by root 5 I. Yeah, we can just like split it up minus 2 by root 5 g. Only we have to do this, then we have to do the same things what we did
Same thing.
above.
Can you
Yeah,
also tell me fx and fy? Don't calculate the whole thing.
fx and f1. Yeah, no issues. Fx will be it will be y squared and fy will be 2xy.
Yes,
Yeah, 2xy. Yeah, correct.
that's correct.
And then finding at 3 minus 3 1, like the du we have to find. So du of f minus 3 1. So then we substitute the fx values, fy values.
Hmm.
1 by root 5 minus 2 by root 5, that thing. And then we get some answer in the end.
Yeah.
Can
Okay.
we quickly have example, look at this thing, that next section, the gradient part. It will be something similar, I feel.
Yeah, the gradient is, but what is this they are saying here? See, now they are moving from 2 to 3 dimensions.
Hmm.
Something like here they are moving. In defining the directional derivative for functions of three variables. This was all
Oh, in
function of
three
two
variables,
variables till
two
now.
variables. In three variables, it will just be like one more extra term
Hmm.
and times a3 if the
Yeah,
unit.
yeah. So
So
fz times a3, correct.
correct.
That's fine.
But both in 3D, no? Like both the equations what we did, like the du of f x0 and y0, like when there was no z0, that was having the 3D. It was in 3D only. It was in 2D
Yeah,
exactly.
that was we were already in 3D. Now
Hmm.
how they will explain this? Like what kind of tangent or what is the physical? I mean, the equation is fine. We extended it,
Ah,
but what is the
equation is
physical
fine.
interpretation of
How
this?
does it look like? Yeah, correct.
So they must have written something. Let's see.
They haven't written much about that. That's the only thing.
As
Somehow they.
before, if A is any non-zero vector in space,
Yeah.
then we define the directional derivative in the direction of A to be this. Okay, A is some vector in space. Earlier, the vector A was in xy plane.
Hmm.
Earlier, we were taking the vector A to be in the xy plane. So some vector A like this, and
Yes.
in that direction only we are looking. Now the vector A itself is 3D. So vector A is 3D,
Hmm.
and the directional derivative along that vector. Directional
Hmm.
derivative of what? Directional derivative of the change of the function f. So I think you cannot draw it. So the basically the function at this point x comma y comma z is some w, and the function at this point is some other value w,
Hmm.
and you are just finding the change divided by the distance h. So that's in that direction. So there can be so many directions in this direction, directions in space. So there can be
Yeah.
directional derivatives in
Directions.
all space. So they haven't said much about this that here. They're just going on to work out this next example.
Hmm.
Should we work it out, or it's a simple extension? So we can go to the
I
sim.
think it's a simple extension. Yeah.
So then they're saying the gradient next section.
Gradient. Yeah.
So by means of the first partials of a function, we can define a vector called the gradient. This
Yes.
vector is important in the analysis of directional derivatives, plays a crucial role in the definition of the plane tangent. So so they so you might come up with something called the gradient because we just now saw. And now I'm going back to the two-dimensional case. Oh, actually no, three-dimensional case. We just now saw du of f, and now
Hmm.
f is a function of all three. 3D case. So du of f is simply equal to f x a1 plus f y a2 plus f z a3. Correct.
A3. Yes. Correct.
So du is a1 a2 a3 a1 I
Hmm.
j.
A2.
So they what they will do is they will say that let us have a vector fx I plus
Fx.
fy.
Yes. Fyj plus. Oh no, that's it. Fyj. And again, that three variable part, it will be fz. Yeah.
Dot a1 I u vector.
Dot a1i. Yes. Ah, because yes. Uh,
So this can be written as a dot product, right? That
it can be yes. Correct.
dot product of two vectors. This is
Two
a
vectors.
scalar, this is vector v1, this is vector v2. Vector v2 is nothing but u, the unit vector.
Hmm.
Vector v1 gets a special name. What is vector v1? It's dou f by dou x I Dou f
Yes.
by dou y.
By dou y j plus dou f by dou z k.
Yeah. So it is a vector of partial derivatives,
Mm-hmm.
and this vector v, so v1 is a vector of partial
Not
derivatives.
v1 is there, and v2 is going to be
It is denoted as delta f.
mhm.
I think that's what they're going to say. Gradient of this denoted as gradient of f. Let f be a function of two variables. Oh, now there are two variables. No, wait, three variables. Partial derivatives, three variables. Gradient is defined as this. This is what we have written ultimately in the last one.
Yeah, yeah, correct.
At that point, so they have evaluated everything at that point also. The gradient
Mm-hmm.
at the particular point. Gradient at different points are different. So they have evaluated fx, fy, fj, fx I vector, fy j vector, fz k vector.
Hmm.
Okay. So it's like
Yes.
how the function is changing in that direction. So you can, and again it's very difficult to view this if the function is of three variables, but it's
Hmm.
somewhat easier to view the meaning of the gradient if the function is of two variables. So
Okay.
coming back to two variables, the gradient is grad f is dou f dou x I plus dou f dou y j. That's it. And yeah, what do I mean viewing it? Let's say the z looks like this.
Yes.
Z is a surface, isn't it? Z is
Yeah.
a surface, and we know so many surfaces in three dimensions. We know that paraboloid, that ellipsoid, that hyperboloid of two sheets, one sheet. All those were surfaces, right? We did earlier.
Mm-hmm.
So I'm just drawing one of them, some paraboloid in three dimensions. Okay, some bowl shaped thing. Okay, so let z be that function. What is the big deal? I mean,
Yeah.
you know,
Correct.
so let it be this case. So what will the
Yes. Yes.
gradient tell you is the
Uh-huh.
gradient is how this function is changing along I direction, how this function is changing along j direction. So gradient is, suppose you're finding the gradient at this point. This point is on that bowl. So gradient
Hmm.
is how you are going along the bowl.
Yes.
Okay, that is the gradient. Okay. So how the function is changing along x plus how the function is changing along y.
Yeah.
So like the physical meaning. But in which direction? You
Meaning is
could go like this, you could go like this, you could go like this, right? So I
that's what
think,
yeah.
yeah, I think I have to read through this.
Okay.
Delta is the symbol. Okay, this is a symbol grad f.
Mm-hmm.
They haven't said anything about that. Gradient of f is denoted by this. So see, it will be a particular vector because fx will be something, fy will be something, fz, and when you plug in the values 1, 2, and 3, for example, you will get some number here. You will get some
Yeah.
number here. You get some number here. So it will be a particular direction only.
Mm-hmm.
Okay, it will not be so many different possible directions. It will only be a one particular direction.
One particular direction. Yes.
Because you have to evaluate this at
That you have
the
to, yeah.
points.
At x0, y0. Yes.
So then they must be saying there must be something. I forgot
Uh,
direction. Okay. So yeah, okay. So we can get the we can get the direction because
yeah.
by again going back to the definition du. So what was du of the function f at the point x0 y0
At x0, y0.
was gradient f dot u, correct? Basically it was
Yeah. Yeah.
fx the component of u a1 plus fy and a2. which is delta f dot u.
Dot U.
So if it so happens, if it so happens that u vector itself, I mean, you can choose any u vector you want. Okay. So u vector, if u vector itself is the same direction as that of the gradient, because the gradient has a particular direction now, right? Because gradient will come out with some values.
Hmm.
Some values will come out according to dou f dou x and x0 y0. Dou f dou x and the point x0 y0. It will come out with some
Zero.
particular direction. It will come out. So if it so happens that u is also the same direction as this, so you choose u to be this. By you have to take divide by the normalizing thing, but otherwise it's 2I plus 3j. Because it has to be a unit vector, you have to divide by 9 plus 4 and square root.
Uh-huh.
Okay, are you understanding?
Okay. Yeah,
So this is
totally.
what we found for this, and then we can choose any u. We chose this u.
We chose that unit vector.
if,
Yes.
if you do that, you find the dot product, what will you get? You get 2I plus 3j dot 2I plus 3j.
Yeah, that will be 4 plus, yeah, 13.
It will be this. You will
Yeah,
get root
13.
13 only.
Uh,
You get
it's the same thing.
root 13 only. If you had taken some
Exactly.
other direction, right? If you had taken some other
Hmm.
direction,
Yes,
suppose you
then
had
it will be
taken the
something different.
direction just I is a unit
I.
vector, then you would have
Uh-huh.
got 2. If you had taken the
A
direction
of
j,
J, like, yeah, y-axis. Yeah, but like it will be 3.
3. Whatever direction you take, only for this direction you will get a maximum value. Root 13 is greater than 2, root 13 is greater than 3.
Yeah, it
You
is.
can, you can try out any other direction.
It will
And
be something small. Yeah, like I plus J. It will be,
so it
what
will
is
be
it? It
2
will
plus
be
3,
1 plus 3. Yeah. Oh.
2 plus 3, 2 plus 3, 2I plus 3.
Oh, okay. Sorry. Yeah, it got cut off there. Okay. Yeah, 2
2I.
plus 3.
So
5 by root 2. So that is also smaller.
whatever direction you take, it will be smaller than this. This, the
Smaller
same
than that.
direction of u will give you the highest directional derivative. So
Correct.
then, so then you can interpret, what you can interpret is that the
Yeah.
direction of the gradient is the
Hmm.
direction of the maximum directional derivative.
Okay. Yeah. Correct. Yes.
So gradient,
The maximum grade. Yeah.
direction of the gradient will give you the maximum, will give you that direction in which the derivative is maximum,
Yes.
in which the change
Correct.
in z is maximum. If
Hmm.
the change in z is maximum in this direction, means that is the gradient direction. I think something like that.
Gradient direction. Yes. No, 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 that's correct. Yeah. Okay. So I understood this also.
This
The
paragraph
gradient.
is telling, from this paragraph they are starting
Ah,
to
that's good.
explain that we see that the largest value of this is the
Yeah.
gradient. The largest value of the
Hmm.
directional derivative
Of
is the
du
gradient.
is the gradient itself. Correct.
The,
Also, if you take that, when I think they just wrote that. So like, yeah, even if you take the dot product, when you're doing a dot product, when you just expand that, you get like magnitude of the unit vector, magnitude of the gradient times cosine of phi, the angle between those two vectors. So if those two vectors had like, if like cos phi, like phi was like more like, oh, I think it was 0, so you'll get 1. So yeah, you can get the maximum value as gradient. And the lowest you can get, I think it's a negative of gradient. The
hmm,
gradient, like negative of the, that the magnitude of the gradient thing.
yeah. So whatever gradient comes out, the
Yeah,
direction opposite to that will give you the lowest, smallest, or yeah, smallest directional derivative, like minus 5, minus root 13.
minus. Yes. Okay.
Oh, so they are explaining this here. Theorem 13 could be interpreted as saying that at x0 y0, at this point, f
Hmm.
increases most rapidly in that direction. F is the z value. F increases most rapidly in a particular direction. Right, pictorially it says f is increasing most rapidly in that direction.
That direction. Yes.
So the graph of f has the steepest incline in the direction of the gradient.
Got it.
A skier would descend fastest by skiing in the opposite direction. Mountain, some example there. Mountain. So the height of the mountain will increase in the direction of the gradient. Height of
Mm-hmm.
the mountain is increases in the direction of the gradient. But the skier
Gradient.
will like to ski along the opposite direction because he wants to get down. Yeah, so like the skier could try to travel along this direction, but he or she may not descend very fast in this direction. Only along this direction
Exactly.
they will descend fast, obviously, right? So that is the direction.
Obviously, it is in fact. Yes.
That is what they are telling about gradient and directional derivative.
Mm-hmm.
Now, what is the next thing? The gradient as a normal vector. What is this? Yeah. Let f be a function of three variables. This is the same thing. This we have discussed.
Yeah. Yes.
Largest value of du and smallest value of du, maximum and okay. The next thing is here.
Yeah.
The gradient as a normal vector. Let
Mm-hmm.
C be a level curve f of xy equal to c. Level curve. F level curve means
Level
f
curve.
of xy equal to c. C is some 10 or some constant.
Ah.
So f of xy equal to c of a function that is differentiable at the point. As the point xy moves along c, the value f of xy is constant by hypothesis, doesn't change. So what is a level curve? Level curve is, wait, so the level curve is something like, see, this is an actual mountain. I'm drawing a mountain. Okay.
Hmm. Yeah, the curve. Okay.
And the height of this mountain is z, and it depends
Yes.
on the x and y coordinates.
Hmm.
The height of the mountain depends on the x and y coordinates. Okay.
Yeah.
It's a 3D figure, so it depends on
3D
x also,
figures.
y also. The height of the mountain depends on x also, y also. So so level curve means those level curve is a, you're joining those points which have the same height.
Hmm.
So it could be like this also. It could be in some arbitrary, it may not be a straight line like this. It could be arbitrary. It's in 3D. It's like this, some sort of circular thing,
Okay.
roughly circular.
Yes. Yes.
So this is the level curve. Level
Level curve.
curve means that the z, the height, which is the f of xy, is held constant to some 10 or 9 or whatever.
Hmm. Yes.
So if a point here is simply moving along this curve, right?
Huh.
You are standing here and you're moving like this, then your height is not changing. Z is not changing at all. Right?
Yeah. Exactly.
You're moving in a horizontal plane. Z is not changing.
Hmm.
Okay. So that is what he's saying. Let x0, y0 be a point on C and assume that it's differentiable. C is smooth. Gradient is not zero. What is this? I was okay. I was looking here. Sorry. Let C be a level curve f of xy equal to C of a function which is differentiable at a point. As the point xy moves along C, right, we are moving along this C,
moving along C. Yes.
The value f of xy is constant by hypothesis, doesn't change.
Absolutely. Yeah.
This suggests that at x0, y0, the rate of change of f in the direction of a unit vector u tangent to c is 0, right? So
Yes.
basically, if you take this particular direction u,
Uh-huh.
so the directional derivative along u at this point, the directional derivative of f
Yeah.
along u is the tangent to the level curve,
Yes.
is 0 because it's not changing. Directional derivative, the tangent. So basically, the tangent is horizontal.
Hmm.
The curve is horizontal. Tangent to it will be horizontal as well. Like if you were to go in that direction, you would be going up.
Ah.
So d along this u would have not been 0,
Would not have been zero. Okay.
but d along this u is 0 of f.
Hmm.
So they're saying that du of f at the point x0, the point is x0 y0 in the direction u. What is u? U is the tangent to the level curve.
Ah.
However, so that directional derivative is 0. However, one implies, now what is one? One implies
Hmm.
that du is 0 for any unit vector u perpendicular to gradient f. Okay, because du of f is equal to gradient f, we have seen that dot u, isn't it? We have seen that the
Yeah.
gradient,
Yeah.
this is equal to dot,
Grading.
and now we are saying along this direction u it is 0, so this is 0.
It is zero.
So therefore we are saying that these two vectors are perpendicular to each other, because only perpendicular vectors will have dot product 0. Is it making sense?
Yeah. 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 Correct.
So therefore the gradient will be perpendicular, gradient direction will be perpendicular to the u direction. Wherever you are, u and gradient will be perpendicular to each other.
With each other.
Combining these results, we can reasonably conjecture that gradient is perpendicular or equivalently normal to the curve.
Hmm.
Whatever that curve is, the gradient is always perpendicular to this curve.
Yeah. Yes.
Okay. So
Okay.
see,
Yeah.
sometimes, yeah, right. Like, it's like here that the gradient is what?
Great. Yes.
So the gradient is always perpendicular to the curve itself. Perpendicular to the curve means perpendicular to the tangent to the curve also.
Hmm. Yeah.
Okay. So that is the theorem here. Let's see level curve. So you
Yeah.
see this level, we are drawing the level curve here.
Yes.
So u and gradient is like this. Gradient and u are perpendicular to each other.
Okay.
Okay. So
Yes, sir.
okay,
So
maybe
next,
yeah, we should stop here.
yeah, yeah. So shall we, like, I think day after tomorrow morning, right?